Something like that. Yeah, like the one I talked about had the quadratic formula in it.
Yeah.
Wanted to work something kind of sort of like that in here. I don't know what's going on with these boards. They're a mess today. I've already like cleaned this like 10 minutes ago, but it's just filthy. So yeah, like the general rule in here is going to be, you can ask me about like problems from the book, examples we did in class, you know, just general conceptual questions. The one thing I won't do is talk about how to solve mission problems. So, because otherwise, all I'll do in here will be solve mission problems.
Yeah.
And there are only 6 of those already, so, you know.
I was like, most of the mission problems didn't seem too difficult. There's only, I think, like 2 or 3 that I was confused by.
Yeah, hopefully.
One thing that, what does it mean by standard angle?
Oh yeah, we can talk about that.
I was like, that was on the first question that I didn't know.
Sure, I can review what standard angle is. I will do that right now. Let me begin with a word of prayer, since I usually do that. But, Heavenly Father, we thank you for this day, and I thank you for all the students who could make it, and I pray that they be blessed by this work, Lord. In my prayer, Lord Jesus, amen. So it's a good thing that at least some students came. If no student came, I don't know what I'd do. So standard angle just means this. Like if you've had a vector in the plane, like A, the standard angle is that's the positive counterclockwise angle measured from the positive x-axis. So like, you know, this is A cos theta, A sine theta, and that's like, the theta is the standard angle in that sense. So when I ask you to find magnitude and direction, in terms of standard angle, I'm talking about that. So like, for instance, just to be specific here, suppose your electric field is minus 10 newtons per coulomb and 10 newtons per coulomb. Like, what's the magnitude and standard angle of this electric field? So the magnitude would be the square root of minus 10, right? And
the standard angle would be just.
So give me a second here. I like numbers.
Oh wait, wouldn't the standard angle just be 180? Or no?
Let's see here.
It would be whatever the arctan of
Yeah.
the opposite.
So that's about 14.14 newtons per coulomb. That's the magnitude. Now, so if you were to use the inverse tangent, you know, it's tempting to think that theta, right? And this, of course, you could also think of this as the x component and the y component, right? So sometimes you think, well, theta is inverse tangent of the y over the x, right?
Yeah.
Except this is only true for a sub x greater than 0.
Okay.
That doesn't always work. And like this one, if I picture, if I picture this electric field goes to the left and up like that.
Yeah.
So because it's.
Couldn't you just do 90 plus 45?
Exactly. Yeah, that's it exactly. That's what I would do. I wouldn't even pick up a calculator. I'd just be like, theta is 90 degrees plus 45 degrees. So like my silly made up example, 135 degrees would be the standard angle here.
Yeah.
But the homework problem, I don't know. I have no idea. You know, you gotta be careful.
I think it was just something. It was just a simple question. I just didn't know what that meant.
Sure.
And then I was confused by one of the examples in the notes.
Where'd that page I had go?
Right here.
Okay, I have it back. Thanks. Yeah. One example in the notes. Yeah, we could talk about that.
I think he talked about it in class and it was just an accidental mistake. But this one right here,
Page what?
right here, right there, it gets squared, so it should just be 3.
Yeah, that should just be
And
3.
then this should be
well,
3, and this should be 3.
I think it was okay down there, but the reason there's a square root of 3 there is that's the unit vector. We're talking about example 1. No, yeah, example 1 on page 5. We talked about this. Yeah, so like the way to fix this is just to erase that square there, then it becomes okay.
And because this is it over just this part right there. So it'd be 1, -1, -1 over the square root of 3. But here it would be 3 then.
Yeah, you're right. That should be 3.
Okay.
Yes. Yeah.
Okay.
Yeah.
That makes more sense.
Sorry about that. Okay, so here, let's work through this problem here. I'm writing this up here.
Sure.
And I'll state the problem up here so anybody watching the video can. We're working chapter 21, number 13 on page 737. And I know you guys have gotten so used to electronic homework you've forgotten these things, but in these textbooks, the odd numbers have answers in the back. So we actually have answers that we can check. So once we work it out, we will hold ourselves accountable to the answer in the back, and I hope I get it right. I don't know, Let's see here. Let's work it out here. So 2113, you have 3-point charges. It's got 2 blue dots on this problem. I'm not sure what that means. So 21.13. All right, so we have 3-point charges arranged on a line. I'll draw the line.
So just a normal line.
On a line. Charge Q3 is at the origin. I'll put that here. And Q3 is equal to 5.00 nanocoulombs. All right. Q2 is minus 2.00 nanocoulombs. Where is that? It's at x equals plus 3.5. So it's like over here. Yeah. It's at x equals to 3.50. What units did they put on us here? Centimeters. Got to watch out for the multipliers. And then the question is, what is Q1? What is Q1?
Does it not get like for it to like remain balanced?
What is Q1? What is Q1 if it is at x equals to 2.00 centimeters? There's more though. It tells us more. Let me read it here. So we have Q1's at 2.00 centimeters. What is Q1? Magnitude and sign if the net force on Q3 is 0.
Okay.
All right. So now, yeah, but you're right. Everything's given here in terms of like where things are. So I'm gonna make this through. I'm gonna make this 1 because it's at 2. I'm gonna put this one over here just to make the picture bigger. Q2. All right. So the net force on Q3 is 0. So let's.
Be when the electric field is equal to 0.
That's true. Yeah.
Okay, so you would just find the electric fields.
Yeah. I mean,
So you know the electric field of 3 is 0, and then you need to find. You can find the electric field of 2.
So your thought is the electric field, the net electric field here has to be equal to 0, right? This is from
The force is 0.
From Q1
And
and Q2, since the force on Q3, right, is equal to Q3 times the electric field due to the other charges there. Great. So, all right, let's think about this. If the
I was going to say also Q1 would have to be positive, wouldn't it?
Yes, right, because so this is, right, so the,
Q2 is pulling, yeah.
right, so exactly. So the electric field from 2 has to be this way, and the electric field from 1 has to be that way, right?
Yeah.
In order for them to zero out, if Q1 was also negative, then we'd have no way to balance out.
Yeah.
Okay, so here we go. What we'll write is we've got K, let's see here, K, I guess I probably should put the distances up here. This is 2.
Yeah, and then it's 1.5 or 2.5.
Yeah, 3.5, like that. Let me think through here. So the, oh rats. So what's the formula for E2? E2 should be K Q2
K, Q2, yeah.
divided by,
The length is just 3.5
Yeah.
squared.
Okay, so 3.5 centimeters squared. And to be clear, I should probably just put the value in here. Q2 is actually 2.
Okay, that's
So-
something else I was confused by.
Well,
Is that because the equation starts out negative? And then that just makes it turn to being positive?
well, I don't know. I mean, it depends on how you want to set things up, but this much I know. If I'm going to make right positive, we draw our picture because the direction of the field, right, the electric field goes into the negative charge, right?
It goes into the negative charge. You mean it goes...
For the -2.
Yeah.
So it goes into that negative charge, the electric field from 2. It's going into the charge, which means that the electric field due to charge 2 has to be going that way. And if I'm going to make that positive, whatever I write here, it should be positive, right? Now there's a way to take this minus and cancel it with the direction vector that I introduced in lecture 1. But there's no need to go through all that. If you just want to like write down, for something like this, I would just write down the equation and do common sense to check that the sign is correct.
Okay.
At a minimum, we should have like a plus and a minus for the different terms. You haven't missed much. We just talked about like standard angle for a second before this. And right now we're working number 13 from the textbook. Once we get done with this, you can ask any question you want. So now Q1 would be minus K. Q1, did we know what Q1 is? Oh, we don't know what Q1 is.
Yeah, that's what you're
Right?
going to find.
But we do know that it's 2.0 centimeters squared, right? And we know that that all works out to 0.
Yeah. Why do you not... why do you not need like the R hats?
Oh, because it's one-dimensional. So like this is all in the x direction, so
Yeah.
no need for it here. Yeah.
Oh, because it would just like equal 1 then, wouldn't it? The R.
Well, yeah, I'm just looking at the x component of the vector. I mean, we could put all of this as like angle bracket this comma 0 comma 0 minus, this comma 0 comma 0, but
Yeah, I get it now.
Okay, so then solve that equation.
Yeah. Okay.
So we'll do that. We've got Q1 equal to 2.00 nanocoulombs times 2.0 centimeters squared divided by 3.5 centimeters squared. And something really cool happens here, which is we don't have to do any kind of unit conversions because you got centimeters over centimeters, so the centimeters cancel, right? And you're just left with whatever 4 times 2 divided by 3.5 squared is, right? So Q1...
Like 8 over... I don't know.
Yeah, I don't know either. I've got nothing to prove. The mathematicians who are impressed by you being able to do this arithmetic in your head, they're all dead now. Let's see here, 2 times 2 squared divided by 3.5 squared.
I got like
Yep. So we've got 0.653 nanocoulombs. Now, I don't fuss too much about like significant figures in my courses. I leave that to the chemists. They got it covered. You know, you don't pay attention to significant figures in your lab. They'll take your points, I'm sure. At least they took mine. All right, moment of truth. This is an odd problem from the textbook, which means we do what? We can check the answer. So, if I can find it. In the back here, what chapter are we? This is chapter 21.
21 and then question
2113. The answer is 0.653 nanocoulombs positive.
Cool.
We got it. Woohoo! I better stick something in here so we can get back to this.
Where did you find that problem was it like in the back or?
So very good question. The way physics books work, the questions are at the end of the chapter. So like, it's page 737. You mind me looking at what you're looking at?
Yeah. This
What is that?
chapter 21.
What is this though? Is this the book?
Mm-hmm.
Oh,
So I went to the.
how hideous. Yeah, let's see here. Past that.
Oh, this one?
No, I think you're. What is that? 21. Look at this. I got 21.13. Huh. Well, keep going. I'll keep going over there.
Version?
Allegedly. Maybe it's under exercises. Oh, isn't that annoying? Oh, look at that.
Oh, here we
Look
go.
at the Q. The Q matters.
So here it is. I was in the wrong section.
No, that's important. So like Q is not the same as 21. There is a Q 21.13, which is not the same as just 21.13. We're in exercises. I'm always interested in exercise. I mean, there's tons to learn in the discussion questions. Don't get me wrong. It's just exercises are where you guys are more likely to struggle. So, okay, so any questions? All right, let's ask a more difficult question. You've got a line. You've got a charge, we'll say Q1 here, and you've got a charge Q2 over here. All right. Then the question is, actually, let me remember what the question is. Just a second here. I'm trying to work through something like the example I skipped in my first batch of notes, you know? It looks kind of scary if you just look at it. I said Q1 is placed here, Q2 is placed there. Where should we place a little q to obtain static equilibrium? All right, yeah. So I've got Q1 there, I've got Q2 there. And now in my notes, I put them at kind of like weird points. But if you really look at the notes, I'm talking about example 3 on page 8 of my first PDF. If you really look at what I do, I start out with vectors, but I quickly go, oh, well, obviously the equilibrium is somewhere in the line segment that connects the two, so we can just, you know, and it basically has to be along the x-axis. So it's not really different than this problem. Let's just make this the x-axis and kind of work out. I'm trying to take away some of the distractions of my note problem to make this more textbook-like for you guys. So here, Q1 and Q2, it's on some line. Let's say that this one is at, we'll say this one's at x. Well, I don't know, where do you want to put these? We can put them wherever you guys want. Let's put this one at 0. Let's put this one at the origin. And let's put this one at L. Just to get away from numbers for a second, let's work a symbolic problem. As a general point of order, it's usually easier to set up your problem symbolically, work it out, and then put numbers in at the end. But I know that's kind of scary sometimes. But it is a good practice to get into. It will. If you play this game right, if you solve one problem, you solve them all. Of course, the bad thing is, as an instructor, if I do this, sometimes students take the wrong idea and just copy my formula down as if some license to solve all such problems. But I usually let them get away with it, so it's my fault. But anyway, so the question is, where in the middle is there equilibrium? Or is it in the middle? Where is there equilibrium? So to keep things, let's start out with the case that they're both positive. All right? So if Q1 and Q2 are both positive charges,
And like the one in the middle, is also positive?
then where will a test charge, it doesn't really have to be a test charge, but we'll think of it as test charge Q, where, I guess I should say, where should we place, a test charge Q to get equilibrium, right? So, which is to say the net electric force on the little q is 0. It doesn't really matter if it's positive or negative. If it's positive, it's being pushed one way by the one and the other way by the other. But either way, we're pushing and pulling. So we got to put it somewhere in here, right? I mean, anyway, I think it's, so here's the thing. If they're both positive, it is clear that the solution we're looking for has to be in the middle. If it was to the right or to the left of both charges, they would both either be pushing or pulling, depending on, well, they're both positive. So they'd both be pushing it away, right? There'd be no equilibrium there. It has to be between. So that's how we set it up. And so we need like a variable that we don't know, because we're interested in figuring out where it is, right? So the basic question is, what's this x, right? That's the question. And if that's x, and this is L, then what does that make this?
L minus x.
Right, L minus x. And then we can just look at the electric field at that point. At this point right here, we know that the electric field is 0, right? So, and we draw a picture. The electric field from 1 is going like this, right? The electric field from 2 is going like that. And I'll let that picture guide my equation, setting up the equation. For one-dimensional problems, I always just think about like a picture and making sure I've got. Anyway, so E1, we do K, Q1 divided by what?
X squared.
X squared, right, simple as that. That's the Coulomb field due to Q1 at that point. If I multiply that by little q, it gives me the Coulomb force at that point due to charge 1, right? And likewise, minus KQ2 divided by what? L minus x squared. And that should all be equal to 0. Now we just have to do the algebra.
I'm a little lost.
Go for it.
Okay, I don't even know how that acts. So where does the K, Q1, and X squared?
Okay, so if we have a charge, the electric field from the charge is K Q divided by like R squared R hat. Your textbook says that. Now in class, of course, I've been using what? I've been doing like KQ over the distance from R minus where the charge is, like squared times the unit vector, like that. These are the electric fields. So like, let me just draw a picture. If I have a charge Q here, and it's positive, then the electric field comes out of that charge in every different direction, radially outward, you know. We'll be talking more about this next week, these kinds of pictures. But so for this one, it's really boring. Like, the electric field comes out of Q2 in all directions, and the electric field comes out of Q1 in all directions. But the distance, you see, from the source point to the field point is just x. So we have kq1 over x squared. I don't need the vector here because it's one-dimensional. Basically, at that point, the r hat is just x hat, or I hat if you like. And likewise for Q2, well, its electric field's going out of, out from it, but it's going out like this. But at this point, it's going that way. And that's why I put this minus here, because it's going to the left. And I'm writing an equation where I'm taking right as positive and left as negative.
So the minus, you just, for the most part, you just look at it, like deciding whether something is negative or positive for these. You just kind of look at it and then you decide.
Yeah, it's a lot like Physics 1 where we have one-dimensional problems. You just kind of have to use intuition to guide how to write it down, because, well, our vector conventions aren't always faithfully followed by the professors and the students in one dimensions. Like sometimes, well, anyway, let me not say that. That's just going to confuse if I go into that. So that's the equation. Now we got to solve it. Cancel the k's, right? And what are you up against? Well, you're up against something like, Q1 times L minus x quantity squared equals to Q2 times x squared. All right? And that's a quadratic equation in x and L and the q's. If you were given specific values of the q's, you could solve it. Let's look at a special case we can definitely solve. So like special case that makes this easy. Q1 equals to Q2, right? If we put Q1 equal to Q2, you already know the answer without doing all this fancy physics. You know that the answer, the balance point by symmetry must be where? In the middle, right? Because where else could it be? And so, but let's work it out. That's L minus x quantity squared equal to x squared, right? So, by the way, you could just flip that. Like, this is a common algebra trick, right? Minus a squared is equal to a squared. And I prefer to think of this as x minus L. It's just for the algebra, it's just friendlier. Because then when I FOIL it out, it's easy. That's x squared minus 2xl plus L squared equals to x squared. Look at that. The x squareds are canceling. It's not really quadratic in this case, right? So these cancel, gone. And what you've got is L squared equals to 2xl. So if we divide by 2L, what do we get? Just what your intuition told you, the halfway point. Let's make it uglier. Let's see if we can do this math when it's uglier, right? So a good way to make this a more interesting test question is, like, instead of putting Q1 equal to Q2 equal to Q, simply make Q2 equal to twice the charge of Q1, right? So like, what if instead of that, I did, so same basic setup, right? But this time, we do Q1 equals to Q, and Q2 equals to twice Q1, right? Or just twice Q. So that doesn't change any of the physics, right? I'm just giving values for Q1 and Q2, same setup, same equation. Now let's see how it solves. So we'd have, Q times, and I'm going to make that x minus L because it's just easier. I hope that's okay. Q2 is 2Q x squared. Then I got to solve this quadratic equation, right? But we can solve it. cancel the q's. You got yourself x squared minus 2xl plus l squared equals to 2x squared, which gives us x squared plus 2xl minus l squared equal to 0, where I just subtracted everything to the other side. Now I'll complete the square. So x plus l quantity squared. Whoa. Dude. Oh, yeah, minus 2l squared. Whew. Whew, for a second there, I felt wrong. It felt like it was a square. That's almost a square, but the thing is that this is not a plus. I thought this was it, but then I was like, well, wait a minute, no. That would have to be a plus for this to be it. You see, if I FOIL this out, I get x squared plus 2xl plus l squared. So to be fair, I had a minus l squared. I have to subtract 2l squared. This is just completing the square. If you don't like this, you could use the quadratic formula. But we should all agree, after we do the algebra, that we get x plus l is equal to plus or minus the square root of 2l squared. We're going to assume l is positive here for the sake of like common human decency. So we got plus or minus like square root of 2 times l. So what we got then is x is equal to minus l plus or minus l times the square root of 2. One of these solutions is physically reasonable. The other one is an extraneous solution. I always tell students if I was to be a rapper, I would be extraneous G, because my tagline would be, I'm not even in the solution set. I got a smirk. Okay. It lands harder in like college algebra for some reason. Like there's certain jokes I tell in different classes just to see if they'll land. And it's a really bad feeling when you tell too sophisticated a joke in like a low-level class and no one laughs. It's like, oops. And it may just be that they refuse to acknowledge it. I don't know. Like they're too cool for it. It could be. I don't know. You need a certain nerdiness to your audience for certain things to work. But one of these doesn't work, right? So like square root of 2 is 1.4. So, well, the minus obviously is ridiculous because it makes x negative, which doesn't work. So we find by physical reasoning, L must be equal to this. X must be equal to the square root of 2 minus 1 times L. In other words, it's like 0.414 L. It's like 0.414 L.
Why would it not just be like 2/3, like one length be 2/3 and the other length be 1/3?
Because it's not. Your question is why is it not at like the 2/3 point?
Yeah.
Because it's not linear.
Okay.
It's because the electric field depends on the square of the reciprocal.
Okay, yeah.
Like if instead the rule was like over x, maybe that would be the case. But it's that squaring is making it. And if you can do this, we could just as well make Q1 equal to like, you can make Q2 like 10 times Q1, right? And you'd know what to do. It would be very similar, but it would give a different answer. Yeah? So we understand that. We're agreeing that we understand it while hedging possible not understanding internally. Yes? No? Understand. Okay. I don't know. You know what I mean. I don't mean to say you have to. I'm not saying that you have to understand it 100,000%. Like, I'm just saying if you understood the words that came out of my mouth, still a little bit uncertain about where this came from. I get that. That's what you're trying to learn right now. That's okay. We'll get there. So what will help that is if we look at a different case. Instead of them both being positive, let's look at the case that Q1 is positive and Q2 is negative. All right? Let's look at that. Look at that over here. Q2, what did I just say? Q1 positive. So you already forgot. You have my problem. It's not good. You're too young. Let's see here. Yeah, I don't think, honestly guys, I don't think we have tutoring here for this class really. I mean, like, there's a relatively small population of students who get through this class with a very good grade, and almost none of those students are interested in a tutoring job. Because like our tutoring center hires people for like, they have to have like 12 hours of work or something. Like, so we would find some people before that might work for like 4 hours a week or something, but it's really hard to find an A student in like upper level engineering who also wants to work that many hours as a tutor. And that's just what's happened here in terms of like how things are arranged. So that's part of the reason I started offering this, is because I figured, this will help you guys. Well, we just never have enough time in class for like all the examples you guys need to see. That's just the case. So we said Q1 was positive, Q2 is negative, right?
Sure.
That was what we're saying. And now we're asking the question, where should we look for an equilibrium point? Yeah? For the sake of, so like when you have a problem like this, which is, so the problem is stated like this. You've got two charges, they're placed on a line, right? And one is to the left and one is to the right, like I have pictured. You can put 0 wherever you want, right? So I suggest, for the sake of specificity, we put, like we were doing before, let's put Q1 at the origin. That just makes things simple to think about. And it avoids the issues which are plaguing you guys in understanding my notes, right? Which is I tend to write more general formulas. Okay, so we're going to put this at x equals to 0. And you know what? We're going to stick with this being at x equals to L, because that will help us maintain a sense of normalcy between this and the last example. But now we think about it. What's the deal? Let me draw a picture. So positive charge makes the electric field go away from it. So it behaves different on this side and that side. Over here, the electric field goes like that. The electric field flows into the charge, into negative charge, flows out of positive charge. This is just the electric field side of the statement that like charges repel and unlike charges attract, because we think about positive test charges always. So anyway, is there any scenario here where they can cancel out to give us an equilibrium? Let's see. Yeah, I mean, let me draw some more here. So like this is, did I even do it right? You guys are probably confused because I should have put 1 both places here. All right, let's try this again. So E1 goes this way here. It still goes this way here, right? And E2 goes this way here, but E2 still goes this way here. So you see, you could have E1 and E2 cancel out on either side, potentially. All right. So let's set it up as if it's over here. And I think if we do it right, we're going to automatically, from the math, get the other one. Okay? But anyway, so let's suppose that we're looking for the point over here just for the sake of setting up everything nicely, all right? We want E to be equal to 0 here. We're looking for the place where the electric field from Q1 and Q2 balances out. We're looking for the place where there's static equilibrium of the electric force. All right, so then what? I've got labels in the way of everything I want to. So like, this is x equal to 0, right? So let's say that this distance is x. Okay, we're going to say this is at x. The specific x. We're trying to find that x. Okay, so that's the distance from Q1, which is one of the sources, to the field point where test charge Q is. What's the distance? What's the other distance involved here? What's this distance here?
X minus L?
Yeah, I think that's it. That's it. X minus L. Cool. Right. So, all right. Let me draw the Q down here just for the sake of like picturing it again. We've got E2 going like this, right? And we've got E1 going like that for this kind of point. And all right, great. So we've got K, KQ1 over that distance, which was what? X, thank you, X squared, and then minus KQ2 divided by X minus L squared, yeah. And that should be equal to 0. Now the question is, I mean, like, so we can't actually solve this for arbitrary Q1 and Q2 except to set it up, and, you know, we can set it up. So this gives us what? This gives us like, you know, we cancel the K's out, right? And we get like Q1 X minus L squared. Yeah, Q2 times X squared apparently. And okay, what happens now if we put Q1 equal to Q2? So let's look at some special cases, right? Special case. Q1 equal to Q2. What do we find there? So they cancel, right? And we're left with the equation X minus L squared equals to X squared. Which, if you take the square root of this equation, you get X minus L equal to X, which gives us minus L equals to 0. Which, if you think about it for a second, makes a lot of sense. Because there is no solution to this problem. If their charges are equal, there's no way you can get a balancing, like, because the left charge is further away than the right charge. If they have equal magnitude, they can't balance out because the left electric field is smaller than the right electric field because that charge is closer. Like, you see what I'm saying? If these are equal charges, the electric field at this point, due to this charge, is way bigger than the electric field from this charge over here at this point. So there's no way they can balance if their charges are equal. The only way that you can hope for balance is if this charge is smaller than that charge. The math should show this. Yeah.
Would that mean there's like a certain like degree that Q2 has to be smaller than Q1? Like if it's Q1 equals Q2, it doesn't balance that.
Yeah, if I'm not careful and
like Q1 and Q2 are very close but not the same, it still won't work?
Yeah.
Okay.
Yeah. Like, if I make this problem on a test, I got to be careful. Otherwise, I can very much... That's why I should always use wording like, if possible, find the equilibrium point. If I just put that as my wording on the test, I'm safe, you know? Okay, so... And I think it's going to matter what L is. Like, so if we work this out, this is what? Q1 X squared minus 2XL plus L squared. Yeah. Equal to Q2 X squared. And so if we rearrange this contraption here, we could rewrite it as like, let's just do it this way. We got Q1 over Q2 minus 1 times X squared minus 2L over Q2 X plus L squared. Oh, the Q1's here too, isn't it? I guess the Q1 over Q2 fraction appears everywhere here. I lost my 2. There's an L. Rats. Go on, ask your...
Wouldn't, for the 2QL over Q2X, wouldn't that be, wouldn't the X be on the bottom as well?
No.
By X squared?
No, I'm not dividing by X squared. What I'm doing is I'm dividing this equation by Q2, which is why I've got this, and that, and that.
Yeah.
And that leaves me an X squared over here. And then I'm subtracting it to the other side, which I've accounted for with this -1.
Okay.
So this is the leading coefficient. This is like the A for the quadratic equation. For it to be a genuine quadratic equation, we need that this is not equal to 0, right? Which is tantamount to what? That's tantamount that we're not in this special case. See, because that being 0 is exactly when Q1 and Q2 are equal. So if they're not equal, this is non-zero, then this will have a solution, although it could be complex. If it's complex, that means that there's not really a solution. So you could actually look at the discriminant, the b squared minus 4ac, and if it's positive or if it's non-negative, there will be a solution. So what I'm saying is if we call this quantity A, and I call this quantity B, and I call this quantity over here C, if I look at b squared minus 4ac, if that's greater than or equal to 0, then there's a solution to the problem. Otherwise, no.
So anything between A equaling 0.
I wouldn't put the problem like this on a test except as like a super challenge bonus question. The way this would appear on the test is like with actual numbers in Q1 and Q2. So you could like actually work it out. Yeah, most likely. Unless, well, I don't know. I think that over here without the numbers, it's not like too bad. Like it's this was, I think this business over here was like a reasonable test question, even though there's no numbers. But if I don't, I'm trying to be careful here. It's harder to, I don't think I can just make, it's complicated for this problem to just, I can't just make, Q2 1/10 of Q1 and hope that it works for any L, because it doesn't. Like the L is baked into the cake of what it takes to make this have a solution. So it's complicated. This would have taken me a whole class period in the other context. Anyway, do you have a question? I mean, we can look at another. Let's look at another book problem. Don't leave me to my devices. You guys should steer me back to book questions. If you want to, you can just look at the list here and see if there's any one in particular you like. We could do one that's like integral, like the line segment kind of thing. There may be one of those to do.
I was hoping we could do one of those because I didn't understand what was happening during class today with the things with the continuous charges over them. So it's confused me.
I'm looking. Now some of these problems you can like use what we did in class to like, work out.
Yeah, just do the same thing.
That's this one. We'll try to do the ones that says calc. All right. Maybe. Goodness gracious. I'm leaning towards either. I think we did 79. If you look at 2179, I think that's very similar to what we did in class. But it's the other way around. That might actually be good for us to do this one. It's the same as we did in class, but the geometry is like slightly different. Maybe that would be a good one to do because I know it's simple. Oh man, these black markers, like I think they're like stale or something. I don't know. I've used about a whole bottle of. I feel like I've used like a whole half bottle of board cleaner to get this marker to come off this week. It's really thick. I mean, it writes wonderful, but it's really hard to get off. Don't ever like get this stuff in your eyes. It's not good. I'll tell you what, though, it tastes worse. I have cleaned boards with coffee before. It works pretty good. It smells better. Maybe I should go back to that. All right, so let's try to start with a relatively easy one here. This is number 79. 2179, and that's page 742. And I will move the camera in just a second, but here's the look of it. This is the y-axis, and they put the charge, a uniform charge Q, like so. All right, and they put another positive test charge out here, Q, and I think the situation here is this distance is A, and this distance here they give us to be R. All right, and it says positive charge Q is distributed uniformly along the x-axis from x equals 0 to x equals to A. A positive point charge Q is located on the positive x-axis at x equals A plus R, distance to the right end of Q. Calculate the x component and the y components of the electric field produced by the charge distribution Q at points on the x-axis where x is greater than A. And then part B, calculate the force, magnitude, and direction that the charge distribution Q exerts on Q. And C, it's to look at the case that it's far away, all right? Which is what I always do in class, you know. Okay, so yeah.
So is it?
Let me move the camera here before I forget.
Is it distributed along a line, or is it distributed
along the line segment? It's distributed in that line segment there. Yeah.
Okay.
So I did this in class, but I did it a little bit differently in class because in class the rod was to the it was to the right of the point where we found the field, if I remember right.
Yeah.
In my notes, it's the opposite. So this might be useful in that sense. So the way we do this is we think about chopping the charge. I think about like an infinitesimal little bit of charge here, dq, right? And I put that charge, I need to come up with a coordinate. So I'm just going to say x is the natural coordinate here to use for that x. dq is at x, all right? And so, and that dq, I can write a formula for it. It's q over a times dx. Why is that? Because the charge per unit length is q over a. We have q, it's distributed over a uniformly, right?
Okay.
So if I take that times dx, it gives me the charge on that little bit.
Okay. Wait,
So like in class, I said lambda is dq dx, which in this case is q over a because it's uniform, and then we solve for dq in terms of dx like that.
Isn't dx?
Oh, where's dx? Dx is like here.
Okay.
It's like this little smidgen. That
It's
little.
Like from like the x to the end of whatever the full charge.
It's the little smidgen of charge that we're looking at. And then you see that, okay, so that little bit of positive charge, it produces an electric field that goes where? I don't even want to draw it because it'll mess up my picture, but if I was to draw it, here's my little dq, right? The electric field goes every different which way out of that little bit of charge. But we don't care about that because we're just interested in right here. So just this one, that's the only one that really matters. The electric field that goes that way out of the charge, dq. So we think about that little bit of electric charge, dE, like that. Then the question is, it's k dq, right? The formula is k dq. So things are getting a little bit easier because I'm not using the 4 pi epsilon naught right now, right? That takes a little bit of the cognitive load out, that I am not using that formula. But it shouldn't be hidden either. So what's the distance from here to here?
A plus r minus x, or a plus r minus x.
Oh yeah, let me just tell you what. Let me be boring and just call it d for a second. So k dq over d squared. That's the formula for the electric field because it's the charge times the constant k divided by the distance squared. This is the Coulomb force, the Coulomb field formula. Same thing we were using in the last example.
So
The dq is equal to q, like is the same thing.
So we have to think that it's dq because it's an infinitesimal charge. It's just a little bit of charge, and we have to add those up to get the whole electric field. Now, I think you might be right about the d. I see some different things here, right? Like this. Let me show you a way you can find your way to that if you don't see what you saw. X plus d is clearly equal to a plus r, right? Because this whole distance is that whole distance. And that you can solve, I think we get what you said. D equals a plus r minus x, right?
And then we're just assuming dx is super small.
Well, we'll get there. We'll get there. Just a sec. We need that dx. So we've got k, I'll put it in, q dx, right, over a times a plus r minus x quantity squared.
But I'm still confused on why for the length does the dx not matter? Is it just because it's super small? Because the a plus r minus x.
Oh, well, we don't think about it's an infinitesimal charge. So like part of it's closer and part of it's further away from the field point, but like we don't consider that. That's the whole point. That is why we consider an infinitesimal charge and not like if we thought about half of the charge, right? If you thought about half of the charge at once, then you'd be faced with a question, should you think about the distance from it here? Or should you think about it from here, or should you think about the midpoint? Well, the midpoint would be perilous because it's not linear. Like you can't just think about it like it's from the midpoint.
Okay.
It doesn't work like center of mass in physics 1 where we can think about an extended object as if it's just at the middle and that automatically works with other things. Like the math is less forgiving here because it's an inverse square law. So we have to take this infinitesimal method, which we do. Now, here's a math trick. I hate minus x, but I've got a square here. So let's trade that for a kq dx over a times x minus r minus a quantity squared. I feel like that's going to make the math better for me. I could be wrong. It probably doesn't matter, but that's what I did. Watch me just create a giant circle of minuses here. But anyway, can you integrate that? See, because the electric field should be the integral from where? From x equals 0 to x equals a of this business. And so that's why the dx matters. You need it because you would be lost. How would you even do the integral without that? You know, I mean, logically speaking, it's got to show up here somewhere. And you can anticipate that. If you think you should integrate over x, there should be a dx somewhere in your formula for the thing you're summing, you know? Now the k, the q, and the a, they're constants, so they come out. And we're just left with the reciprocal, the square function. That integrates to minus 1 over x minus r minus a. You evaluate that sucker from 0 to a, I believe. Now you can test me, am I right? If we differentiate this, what happens? We've got the reciprocal function, so like the derivative with respect to x of 1 over u is equal to minus 1 over u squared times du dx, right? That's the